And the journey into Chapter 6 continues. In the last video, we discussed how different bases for the same space give us, for each vector or point in that space, different ways of representing the vector, and therefore different coordinates for the vector. And then we went on to discuss the problem of translating a vector's coordinates relative to one basis to the same vector's coordinates relative to another basis. And we found that this can be accomplished by a change of basis matrix, and we learned how to compute what such a matrix would look like. If any of that is unclear to you, please go back and review that older material because we will need it today as we go a little further down this path. Because today we will be talking about what the matrix of a linear map looks like relative to a non-standard basis. Up to this point, whenever we have talked about the matrix of a linear map, we have always assumed that any vector we feed into that matrix is represented by its standard coordinates, and that the vector that emerges as the output is also given in standard coordinates. And of course we made that assumption, because for the first 5 chapters of the book, the only basis we really worked with was the standard basis, which means that we could afford to be sloppy and think of a vector and its standard coordinates as essentially equal. But as we now know, that's not quite right. The vector is the geometric object, the thing in and of itself, whereas its coordinates are a particular list of numbers that we can liken to the way we would describe the actual thing itself in a particular language. If we speak standard, the E language, or let's just call it English for E, then we would look at this vector and say, aha, that is 3, 2. Whereas if we speak some other language, we use some other basis, which I'll call F here, we would look at this exact same vector and say, in our F language, oh non, il est un. Mon Dieu. And we would be sure that the Englishman who called this thing 3, 2 has it all wrong. But we, of course, are learning to rise above such petty national squabbles and recognize that the vector itself can be represented in many different languages or bases. So far, so simple. But just as a vector can be thought of in several different and equally valid ways by using different languages, different bases, it is also the case that a given linear map, a linear transformation of a vector space, can be represented by very different looking matrices with totally different numbers inside of it, which will depend, again, on the language, on the basis we use to describe what is going on in that space. And so just as we had to make a distinction between a vector, the thing in and of itself, and the coordinates of a vector relative to some basis, we're going to do the same with linear transformations. The idea that distinguishes these things is that on the one hand, we have the linear map itself, a geometric action that takes place whether or not we are observing it, whether or not we are describing it. And then on the other hand, we have the map's matrix relative to some particular basis. The matrix is a way of describing this map in words, or numbers as it happens, and thus is dependent on language, each of which shows the subject from a different perspective. But anyway, what do these objects, this map and its matrix representation according to a specific basis, do? Well, we know what a linear map does. You start with an input vector, pass it into the linear map, which turns it into some other vector, the output vector. And naturally, the matrix representation of this map should do the same thing, except everything is going to be described in terms of this basis B, the language in which we're operating. So the idea is that not the geometric vector V, but its description relative to basis B, its B coordinates. We're going to take that stack of numbers, hit it with a certain matrix, the map's matrix relative to the basis B, the way we describe it in that language. And what we get out will be, of course, the output TV, except since we're speaking in the B language, which in the book I refer to as Bulgarian, what we get out will be not just the geometric vector TV, but rather its B coordinates. So everything is happening in Bulgarian. Somebody else who is watching this vector get mapped by this transformation into this new vector would describe all of these things in different ways, because they would be using a different basis, the English basis or the French basis or the Icelandic basis or the Chinese basis or whatever it might be. But now you see at least what this thing is supposed to do. T's matrix relative to basis B is the matrix that turns vector V's B coordinates into vector TV's B coordinates for all vectors V, or at least those that can function as inputs to this particular linear map. And I'll record that up here for future reference. And this prompts a question. What do the columns of this matrix look like? When we are working with the standard basis, we know what the columns look like. They're simply the images of the standard basis vectors, expressed, of course, in standard coordinates. Based on that, it's a very reasonable guess that the columns of T's matrix relative to some other basis will be the images of those basis vectors in the coordinates given by that basis. And your guess would in fact be correct. But let's go ahead and prove that, mainly just so that you get some practice thinking about the notation and review of matrix vector multiplication and all that kind of thing. So let's let basis B consist of vectors B1, B2, all the way through Bn. Now let's think about our typical vector V. Let's suppose that V has the following expression in terms of the B vectors, so that V's B coordinates are C1, C2, all the way down to Cn. So ultimately, T's matrix relative to B, this is the thing whose columns we seek. We know that we are going to take this coordinate vector, V's coordinate vector relative to B, feed it to this beast, and in return, it will give us the B coordinates of V's image. So we'd better think about that image next. If this is V, then we know something about TV. Namely, it is T of that linear combination. And then, thanks to the linearity properties of T, we can rewrite all that stuff as this. Okay, so now we have an expression for V's image. But what we want this matrix to produce is V's image expressed in B coordinates. Well, all right, let's just rip the B coordinates from both sides of this equation, like so. And now on the right-hand side, we will appeal to linearity again, the linearity of this coordinate ripping operation, which we discussed in the previous video. It tells us that we can rewrite this right-hand side as this. So now we have a nice expression for the B coordinates of V's image. That's what we're looking for, because it will be the output of our matrix that we want. But our question was what the columns of that matrix look like, and we should be able to see that pretty quickly from this equation. We know that any linear combination of vectors can be rewritten as matrix vector multiplication. If I do that here, that right-hand side becomes this. I've got a matrix whose columns are the vectors in this linear combination, multiplied by a vector whose entries are the weights for those columns, namely C1, C2, and all the way down to Cn. But wait a second, we've seen that before. Those are the B coordinates of vector V. So I could rewrite this last expression as that matrix times vector V's B coordinates. Ah, but look what we have now. Look what this matrix has done. This matrix is turning V's B coordinates into TV's B coordinates. And that is exactly what the matrix we want is supposed to do. So that means this guy right here, this is linear map T's matrix relative to B. Now we can answer our question, what do the columns of that matrix look like? Well, we're staring at them. They are, precisely as we guessed before, the images of the B vectors expressed in B coordinates. And that is what you want to remember here. Don't try to think of it in terms of these awful symbols with brackets and subscripts of subscripts and so on and so forth. Let's summarize what we have just discovered here. If T is any linear map, then its matrix relative to a basis B is denoted T in brackets with a subscript b, and its columns, as we have just proved, are the images of b's vectors expressed in b coordinates. And there we have it. And notice that what we learned back in chapter 3, when we were only working with the standard basis, is just a special case of this more general picture. In that special case, we would still have a linear map, and we were just finding its matrix relative to the standard basis, E. We didn't use this notation because we didn't have different bases among which we had to distinguish. But its columns, of course, were the images of the standard basis vectors. And of course, we expressed them in standard coordinates because that's all we were working with. This merely generalizes that to any basis. It's still not completely general because, although I did not write this explicitly here, it only covers the case where the input space and output space of our linear map are the same. Like, say, a map from R3 to R3, or from R10 to R10, or from some subspace of a larger space into itself. After all, in the situation I'm describing here, we're using the same basis for the input space and the output space. Now, you can generalize this to cases where that's not true, like if you have a map from R3 to R5, but then you would have to talk about the matrix of that map relative to a particular basis of the input space and some other basis of the output space. It still works basically the exact same way. The columns turn out to be the images of the vectors in the input space, except you express them relative to the basis of the output space. But we don't need that level of generality here, and I think that if we keep it at this level, it will be easier to understand as we're getting used to it. So it's high time that we consider a specific example. To maximize the intuition we can bring to bear on a problem, let's consider a linear transformation of R2. And in particular, let's look at the line y equals minus 1/3 x, and we will let f be a reflection over this line. That is, of course, a linear map, so now I will pose a fairly open-ended problem. Find a matrix representation of f relative to some convenient basis. And you might say, well, the standard basis is always the most convenient, so let's do that. We just have to figure out what the images of I hat and j hat are. That's a little tricky. It's definitely doable, but it would require a little unpleasant analytic geometry. Think about the second column if we were trying to do it with a standard basis. We've got j hat. Where does it get mapped to? Where does that point 0, 1 get mapped to? Well, it gets reflected across the line to somewhere over here, but where is that exactly? What are the exact coordinates? There are different ways to find out, and it's a great exercise for a pre-calculus class because you'll probably want to figure out the equation of the line that passes through the tip of j hat and is perpendicular to the given line. And then I'll leave it to you, if you want to pursue what you would have to do from there. As I said, great exercise in analytic geometry, but it's a bit of a pain, and it's unnecessary because we weren't specifically asked for a matrix representation relative to the standard basis. We weren't looking for the standard matrix representation. We just want a representation relative to some convenient basis. Maybe another basis would be more convenient because it would be much more obvious where its vectors get mapped by the reflection over that line. Can we think of such a basis? Well, sure we can. For example, suppose we take a basis of R2, one of whose vectors is this one, which actually lies on the line of reflection. Let's call it B1, and so that we can work with nice whole numbers, let's say that B1's standard coordinates are 3, minus 1. We know that that point, 3, minus 1, satisfies the equation of the line, so this will work nicely. And the reason why this is a very convenient basis vector for us is that we know exactly what happens to it when we hit it with the reflection. It doesn't move at all because it's on the mirror. There's no mystery like what happened to j hat when we reflected through that line, or I hat when we reflected through through that line. B1 just stays put. There's no mystery at all. Okay, and to fill out our hopefully more convenient basis for R2 with regards to this particular problem, let's just take the vector we get if we rotate B1 90 degrees around the origin. That gives us this vector, which we will call B2. And this will also be convenient because we know what happens to it when we reflect it over the green line. It just becomes the negative of itself. So there's a sense in which this new basis we've come up with seems much more suited to the reflection with which we're working than the standard basis did. Collectively, we'll refer to that basis as basis B, and although we could certainly write down B2's standard coordinates like I did with B1, I don't actually need them for the task at hand. I'll need it a little later. So for now, let's go ahead and see if we can write down our solution. The matrix representation of F, our flip over this line, relative to our hopefully convenient basis B will be, well, let's see. The first column of our matrix will be what? We'll go back to the thing we proved before. The columns of this matrix are the images of B's vectors expressed in B coordinates. So the first column is the image of B1 expressed in B coordinates. Well, the image of B1 after we flip it over the line is still B1. Okay, so the first column is just B1's B coordinates. Well, that's easy. To get B1, how many B1 and B2 steps do we have to take? Obviously, we take one B1 step and 0 B2 steps, and we have our first column. What about the second column? According to our theorem, that is going to be the image of the second basis vector in B coordinates. Well, the image of the second basis vector is clearly just the opposite of B2, because that's what we get when we flip it across that line. What are the B coordinates of that flipped vector? Well, how do we get to it in terms of B1 and B2 steps? Obviously, we take no B1 steps and negative 1 B2 steps. So that means the second column will be 0 minus 1. And that's that. We have found a matrix representation of F relative to a particular basis. And just to show how it works in practice, let's look at this vector, which I'll call V, and let's assume, as it looks, that V's B coordinates are minus 1, 1. We take one step in the negative B1 direction and one step in the positive B2 direction. Of course, if we reflect this vector over the given line, we're going to end up with something like this, which would be f of V, and it's pretty obvious that f of V's B coordinates would be minus 1, minus 1, because we'd have to take one step in the minus B1 direction and one step in the minus B2 direction. I just want to point out that that minus 1 is what we would get if we just thought about it algebraically, because algebraically speaking, if we want the B coordinates of f of V, we should be able to compute it this way. Start with V's B coordinates and hit them with the reflections matrix representation relative to B. And when we fill in the specifics there and carry out the product, we do indeed get minus 1, minus 1 as the B coordinates of the image, just like we said we would. So this is just to show the algebra that's happening in parallel with the geometry. But someone might fairly object, well, that's cute, but who cares about this basis B? I want to know how to represent this reflection in standard coordinates because that's what I usually work with. That's a perfectly good objection, and I have good news for you if you want to make that objection. One of the main reasons we think about matrices relative to non-standard bases is that they can help us come up with standard representations of linear maps. And this is where we can start to connect the ideas we're talking about today with the ideas we discussed in the previous video. Let me go ahead and pose a second problem. Let's find the standard matrix representation of F. And I am going to need a little more room, so I will eliminate this stuff, which by now is surely in your notes already. So let's see. Before we write up our solution, I want to haul you off into a corner here where we can discuss strategy informally and privately. We're looking for the standard representation of our reflection. So we want some mystery matrix that will take the standard description, the English description, so to speak, of a vector, and through matrix vector multiplication, we'll turn it into the standard or English description of the vector's image. How are we going to find such a matrix? And you might say, oh, if only we knew Bulgarian, life would be much easier. We already have the matrix that turns the Bulgarian description of a vector into the Bulgarian description of its reflected image. But hey, if you can solve it in one language, you can solve it in another. Or at least you can if you know how to translate between those languages. And you do know how to translate between those languages, because that's what a change of basis matrix does. So our general strategy here for finding a matrix that does this is that if we are given an English description of a vector, the first thing we're going to do is translate it into a Bulgarian description. Then we will feed that Bulgarian description into this matrix, which solves the problem in Bulgarian. It will give us a description of the reflected image of the vector. The only problem is that it too will be in Bulgarian. And that's not what we want. We want the English description of the vector's image. Well, that's fine. If we have the Bulgarian description of the vector's image, all we have to do is translate that into English using another change of basis matrix, a Bulgarian to English change of basis matrix. I hope this makes sense. The idea is we just take the problem we have, translate it into another language where we know how to solve the problem already, and then translate the solution back into English. So let's do a little more scratch work while we're over here in the corner, just to be sure we know exactly what we're doing. So we start with our English description of a vector. Then we use a change of basis matrix to change its English description to a Bulgarian description. Same vector, just different language. So all that stuff is the vector in Bulgarian. Great. We're going to feed our vector in Bulgarian into that matrix. So that means we'll multiply this thing on the left by F's matrix representation relative to B. Well, you feed a Bulgarian vector to the Bulgarian description of the reflection, and of course, the result is a Bulgarian description of our original vector's image. Well, that's very close to what we want. All we have to do is translate from Bulgarian to English. Well, if C is the English to Bulgarian translation, then the Bulgarian to English translation is just C inverse. So now we're taking all this stuff, which is the Bulgarian description of the image vector, and we're simply translating it from Bulgarian to English. So the net effect of all that is that all this stuff is the English description of the vector's image. And so now we've done it. We were looking for a matrix that transforms the English description of a vector into the English description of its image. Well, here it is. This crazy looking thing does precisely that. So that means that this thing is F's standard matrix representation. And if you understood that much, you understand this general topic, because the rest is just carrying out the computational details, which are easy. And notice how the thing we were after, the standard matrix representation, we ultimately obtained from this non-standard matrix representation by surrounding it with a certain change of basis matrix and its inverse. I believe in the book, I liken this to putting on a pair of headphones so that what was in Bulgarian, you hear through the magic headphones as though it were in English. This is not something to memorize. Rather, it is something you just think your way through whenever you need it. Let's do it once more quickly, just so you see how we end up doing something like this on the fly. Then we'll go and actually write down our solution carefully. We're looking for F's standard matrix representation, this guy. Well, working through the logic in our heads, we think, well, we are ultimately going to rely on this Bulgarian matrix, even though we're going to arrive at an English solution. But what we're going to do so that we can start in English and end in English is first translate from English to Bulgarian, then do the transformation in Bulgarian, which will give us a Bulgarian answer, which we'll then need to translate back into English. So again, nothing to memorize here. Just think. And once this whole line of thought has occurred to us, the rest is just easy computation. So let's actually carry out our solution. I will begin with this little equation that we just wrote down, which we thought our way through very naturally. And this tells us that the matrix we want is just the product of three other matrices. Well, we already have one of them, so now we need to get these change of basis matrices, and we will be in business. one of them should be easy, and then we can get the other one by taking the inverse. Actually, the easy one is going to be the B to E change of basis matrix. So you know what? I'm going to make a little change. I'm going to call that matrix C and call the other one C inverse. That will just make my notation a little cleaner. Anyway, let's see. So C is the B to E change of basis matrix, and we know how to find such a change of basis matrix. Its columns are the vectors in B expressed in E coordinates. So let's start with the first vector in B. Well, we've already said that its standard coordinates, its E coordinates, are 3 minus 1. Good. So now we need the second column. That's the second B vector expressed in E coordinates. Well, what's that? We haven't actually written that down. Do you remember quite some time ago, I think it was in chapter 3 or maybe even in 2, I showed you a little trick, which was that if you have any point, I'll call it xy, in R2, then if you rotate it by 90 degrees counterclockwise, the new coordinates will always be obtained in a simple way. You reverse the coordinates and negate the first one, so that if this point was, say, 5, 2, this point would be minus 2, 5, which certainly looks plausible, and it comes down to these two right triangles. And I'm not going to go through the argument again. We did it once before, and if nothing else, I believe I have it as an exercise, the current section. So I will leave it to you to explain why that is so, and I'll simply use it here. That useful property tells us that if this point right here has standard coordinates 3 minus 1, then this one right here must have standard coordinates plus 1, 3. So those will be the entries in the second column. Good. And so I don't forget what this is doing, I'll write under here that it's the B to E change of basis matrix. Well, I have two of the matrices I need to compute this product. Now I just need the inverse of the matrix I already have. But that's easy. It's a 2 by 2 matrix, and everybody knows how to invert a 2 by 2 matrix. So C inverse is, well, remember how it works. First, we're going to get a scalar, which is the reciprocal of the determinant of our matrix. Well, the determinant is 9 minus 1, so 10, which means I'm going to get 1 over 10. And then I've got, for this 2 by 2 matrix, well, let's see, the off-diagonal entries are both negated, so they change their sign, and the two entries on the main diagonal switch places, which in this case doesn't actually make any difference at all, since they were equal to begin with. So we have our matrix C inverse, which of course is the E to B change of basis matrix. And anyway, now we have enough information to write down the standard matrix of our reflection over that line, because the standard matrix representation, we said, is going to be C times F's Bulgarian matrix times C inverse. Now we know that we can pull this scalar out to the beginning through all of the matrices, so let's do that to keep it neat. And now all we have to do is a bunch of multiplication. Matrix multiplication is associative, so it doesn't matter whether we multiply those two first and then multiply the product by that, or multiply those two first, multiply their product on the left by that one. I will do those two first, and when you multiply those out, you'll find that they are equal to this, but we still need to multiply that by the rightmost matrix, and when I multiply these two matrices together, we get this, and we are done. If you like, you could push that 1/10 into the matrix and write it this way, but I think that's very ugly, so I will leave it factored outside. Much nicer to have all whole number entries. We just have to remember that the 1/10 really is part of our matrix. Good, and that's it. We have now succeeded in solving our problem. We have the standard matrix representation of a reflection over the line y equals minus 1/3 x. In the book, I work through another example where instead of a reflection, we are looking at orthogonal projection onto a line in R2. Then you have many examples, of course, in the homework problems. But if you understood what we did here, really thoroughly understood it all, then you have the idea. There's not that much to it, although it's built on a lot of different ideas. So we have come a long way, and all packaged together, it's a very powerful idea that we can solve what seems like a difficult problem by figuring out a way to solve it from a different perspective, using a different basis that makes things much easier. Then all we have to do is translate into that basis, do the hard work there, and then translate back out so that we end up with our solution in a language that we actually want it in. It's really a common technique throughout mathematics. Take a problem that you're given, transform it into an easier problem that you can solve somewhere else, solve it over there, and then translate the solution back. Well, let's see. Is there anything else I have to say about this? Oh yeah, just out of curiosity. Well, first, let me clear out some space. That's better. As I was saying, just out of curiosity, remember we started out when we first looked at this problem asking, where does j hat get mapped by f? And we were thinking about, all right, here's j hat. We know it gets shot across this line of reflection, but what exactly will its coordinates be? And we said we could figure it out with some elementary analytic geometry, but it would be a bit of a pain. Well, now it should be very easy for us to write down an answer, because now we have the reflection's standard matrix representation. So where does j hat get mapped by f? Well, we take f's standard matrix representation, multiply it by j hat's standard representation, and that will be that. So if we write down those two representations, we have a very simple answer. This matrix vector product, well, let's see, it's 0 copies of the first column and 1 copy of the second column. So we just get -6, -8, but we still have to multiply by a 10th. So we end up with -0.6, -0.8. And that is where j hat gets mapped. And you know what? I think that is enough for this video. It has been a short video for a change, and I think that's good now and again. So read the book, do the exercises, and I will see you next time when we will talk about linear isometries. What are those? You'll see. And actually, this map F is an example of one. And we will talk about orthogonal matrices with which they are intimately related. So until then, good night, good morning, good afternoon, or whatever time it is where you are.